Our next presenter is Moses Bomera, a colleague who I work with on day-to-day. So because DevOps is beyond just normal, it's beyond building pipelines or managing cloud environments, but we're also looking at machine learning operations, right? So this keynote is, this session is really focused on that. So at this juncture, I would request our next presenter, Moses. The floor is yours. Once again, we are powered by Emata JetBrains, Nairobi DevOps community, and also we also give a vote of thanks to AWS for the in-kind support around ensuring that we attendees gain skills through Skill Builder and through certifications. Yeah. At this point, let's get Moses online.
All right. Good morning, everyone. I hope we're all doing well. Let me share my screen.
Yeah.
Okay.
Yeah. Also brought on your screen. Please take it on.
All right. Good morning, everyone. And as Stephen mentioned, this talk will focus a little bit more on the machine learning side and data management with a DevOps in a bit of the background. My name is Moses Bomera. I do work with Stephen at Emata. I'm a data scientist. All right, and today we're going to have a discussion about lakehouses and how they can be used in machine learning applications, what they are, when you need them, etc. So before we define what a lakehouse is, we need to think about the workloads that will lead you to using a lakehouse for your data management. A lakehouse is really just, it's an architecture that provides certain properties that you can use to manage data. And if the workload that you're working on does not meet them, then a simpler storage would be the thing to choose, as opposed to dealing with the complexity of what comes with managing a lakehouse. So what are some of these? What are some of the things that we can use to determine that we actually need to use a lakehouse as opposed to, say, a regular transactional database? So if you find that the workloads that you deal with need several different systems to read them, think of systems as maybe there's a team that uses Python to read this data, or there is a business intelligence team that is using the BI tools to read the same data. Those two teams could be using different engines, and a lakehouse would be a solution for that, like something that provides one single source of data that allows multiple different engine systems to actually read this data. Then if you are looking to reconstruct the data used, so think of, you don't just care about what the data looks like today, you care about what the data looked like at a certain point in history. That is by far the biggest signal that you need a lakehouse. So if you query the data today, maybe it looks like a certain thing, and then maybe 1 year ago it looked different, etc. That is where you'd get the most value in using a lakehouse. Most of these other properties can be achieved with medium to relative complexity with regular DBs, but the table state, i.e. what the table looked like, what data was in, what the rows look like, etc. That is like the forte of what lakehouses give you. Then if the workloads you're looking at require a lot of writing, not really upsetting, like changing something that is already there, but just appending data, then you're also looking at a lakehouse. That's something that could help you manage such an application. And then a schema change. So think of, I want to add a column to a table or remove it. And I have so many consumers, like we looked at in A, where you have so many people reading different things from that same data. Maybe the machine learning team needs only 3 columns from that data. The business intelligence team needs maybe 5 columns of that data. So the lakehouses allow you to change this without affecting all the people that actually feed from this data. The people that need the new columns will include that column on their side and get it. Those that don't need it will remove it. Again, this can also be achieved with a transactional DB, but yeah, in this particular case, this feed is specifically built to support this. So seeing where we can use a lakehouse, there are also scenarios where a lakehouse is the wrong fit to use for whatever it is that you're working on. So if I use an example of this session, say this session had an application and you can ask what time is a certain session, you would not want to use a lakehouse for such a thing. A transactional DB like SQL, PostgreSDB, etc. would be the thing that you'd actually use for that. Lakehouses are built more for where you want to query for batches of data, batches in millions of rows, etc. But if you want point lookups, single row querying, then that is an OLTP system. Then if you do a lot of writes, like as the application is running, maybe it's changing state somewhere, your customers put something in their cart, etc. Again, a lakehouse is not for that. A lakehouse is for the bulk writes, bulk reads. And if the data set that you're dealing with is really, this is relative, but it's something that can be small, can be handled within a regular DB, then you can get all the benefits of a lakehouse with a bit of building some features around the DB, but you can get it with a regular OLTP system. All right, so the key point of deciding to use a lakehouse is really the reconstruction I talked about. It matters to you that what the data looked at a certain point in time can be reconstructed. That is really the biggest driving force why you need this. And this is very important in machine learning. Think of it this way: you could train models, say in the first quarter, and the data looked a certain way. Maybe in the second quarter, some changes were made to the historical data, but you're still running a model that was trained using the old data. So if you're going to do any evaluation to see if the performance has degraded, you cannot use the new data. You'd have to go back in time and use the state of the data at the time the model was trained. So that is by far the biggest gain you get with using the Lakehouse architecture over the regular OLTP systems. All right, so we're going to break down the Lakehouse into the different components it is, and hopefully by the end of this talk, we have an understanding of what a Lakehouse is, when it can be used, and some of the applications that it can be used in. So at the core of a lakehouse is something called a manifest, and you can think of a manifest as something that describes metadata that describes the actual data. So, and it's that manifest that whatever the reader or the system writing to the system, to the lakehouse, will always refer to before it can actually execute any queries on that particular data. An analogy I can make with with a manifest is I think we're all familiar with how Git manages changes in code. At every time you make a change and commit it, something is stored that points to that state of that code, that particular commit. And if you ever wanted to see what the code was before that commit, then you simply move to that particular commit. So it's the same with the Lakehouse. All the data that gets written into the Lakehouse literally has a commit in the. So let's think of this box with the metadata as the manifest. It records whatever happens in the table, and it's stored separately from the data itself. So the data is never touched, as it's immutable. You write it, it stays that way. It's the metadata that is updated to show the latest state of the data. So with each write, a new metadata file is written, and it will describe the now current state of the data. I hope that starts to paint a picture of the whole point in time provenance that the lakehouses provide, because the storage of the metadata with the whole manifest logic is how lakehouses are able to achieve that particular property of being able to move back in time and recreate data as it was then, as opposed to what it is today. Yeah, this is more of a demonstration of the same. So you write some data to be stored. A manifest pointing to the metadata's description will be stored along with it. And that manifest literally just contains some statistics about the data, how many rows were written, how many are missing data, etc. And to access this, you'll need something called a catalog, and that catalog is just a pointer to what the latest version is. So if you, the systems do allow you to keep a track of the different versions of the data. So whenever you point at a different version of the data, you'll get whatever the state of the table was at the time that you were actually, what the table was at the time the data was written to it. So the manifest, along with the metadata and the actual data being written and being immutable, give you the three properties that allow for workloads that benefit from things like this. That's mostly machine learning, where you want to know the different versions of the data that you've used to produce the artifacts. That's the models, the prediction, etc. So one is the time travel. Thinking of it the same way with like a Git repo is you could literally go back in time and see what the code was when the repo was just created up to the point of where it is today. The other is a schema evolution. So the manifests get edited, but the data doesn't. Think of it as, say you have a table that has 3 columns, then you add a third one. Sorry, it has 3, and then you add a 4th column. The Lakehouse enables you to, along with time travel, you can go back in time and query that table and see what it was before the 4th column existed. And then you can also query the current state and see the different version with the columns existing. Then, like we saw, there's also the querying engines can be as long as the query can read the manifest, then any engine really can read this data. So these are the things that Lakehouse gives you. And they're also things that you will not get from using a system like this. So it's not a database. It's just pure storage of data that uses a table format that defines all those features that we've talked about, the schema evolution, the time travel, etc. But at the core of it, it's simply really object storage, or you can really store it on a disk, and a defined table format that structures how the data is written, how changes are made, where the different data components are stored. So when it comes to the querying and everything, then you would have to use an external system. Like in Python, you could use DuckDB or Polars etc. Those are really tools, but The lakehouse is simply the storage of the data. Then, like I mentioned before, if you care more about single row querying, that is point lookups, indexing, etc., this does not provide it. The metadata that we saw does not really record details about individual rows, but more of about groups of data written. It can get close to a row, but then we'll be using it for the wrong workload. If a point lookup is something that the workload needs, then you're looking at a transactional processing system. Then there are no cross-table transactions. Think of like in Postgres or in an LTP system, you can write to more than one table and guarantee that that transaction can only end after all the tables have been updated. In a lakehouse, you only get that for one table. So if you need to guarantee that if something is written in one table, it's written in another, you would have to add extra guardrails to something like that, or use the system that inherently supports it. Yes, then writing in the, like updating the tables does not change. See if you can see it on this diagram. Like when you add more data, because the files are mutable, a new version, a new copy of the data is written. So whatever exists stays existing. It's just that another data file gets written and the metadata or the pointer moves to that version. So if a crash happens when something's being written, then you'll have to do a cleanup of the half-written data, but the commit itself will not have happened. So the data itself stays safe, but there is a maintenance job up there to actually remove what failed. So the core point of the Lakehouse, again, is provenance. That is, you have data and you want to follow it from whenever it appeared in your system to, say, a decision that you made upon that data. We'll use a few examples as we go ahead so that we can connect a few bits and pieces here. But in a machine learning world, normally there are three things that you are building. There is the code that defines the models, etc., and that is managed with a version control. Then there are the models that are built out of the data that you have. These two have their own versioning. You can use registries, tools like MLflow, etc. And then there is the data that those two things bring together. So the code will define the training pipelines for a certain, say, objective. Maybe we're trying to focus something. We have a data set. We're trying to produce a model. So a lakehouse gives you a close enough, should I say, feature of version control for your data. Yeah. Imagine you have like a forecasting run. Maybe you're forecasting something, and with a regular version control for the source code, you can well find out which code that you used to train the model, what parameters you set, etc. You can also store the model that was actually produced by that. But equally important is the actual data that produced that particular model. Like I mentioned, data can get corrected after some time. Maybe it was wrong or it was placed in, I'll use an example of farmers, which is something that we work with a bit. Maybe there could be a period where a farmer had a gap, and then you trained a model with that gap, made that assumption that they didn't make any deliveries. And then later in time, you find out that that data did exist and it's now added. Now, if you query at that point in time, it will seem as if the gap never existed. Yet the model remembers that there was a gap. So to keep all the things aligned, to find out what the actual state of the data was, you can get that from a lakehouse, as it gives that provenance, as we've seen. Like you'll have trained your model with a certain, I'll call it a commit, but a storage of the metadata of around that time. And if you point back to that, then you'll get what the data was at that point. And if you're doing any evaluation, then you're doing it with the context of at the time this model was produced, at the time I used this code, the data looked this way. If you evaluate it against what the latest state of the data is, then you're getting the wrong readings from your own data. All right, we have talked about that, and yeah, so when data is written, the equivalent of a comment here is a snapshot. That snapshot maintains or tracks the state of the table at that particular point in time. As we'll see later on in the future, these snapshots, as they grow, can also become an issue. So you need to have some kind of maintenance around them. But ideally, as long as you need to remember something, then you keep a snapshot of it. Then looking at this, so critically on what a snapshot could be with the concept of time travel. Let's say at a certain point, let's say snapshot 1 is July, and today we are in August. And we have the table with these 4 columns. Then at a certain point, maybe at the start of August, we added another column, and now the table looks like this. So if you query today with today's snapshot, you'll see it this way. And if you went back to the snapshot of July, then you'll see it without those columns. This is really similar to, again, the analogy with Git commits and what it gives you in terms of checking state of things at different points in time. For machine learning, again, this is very key, and data science workloads. You want to know what the data was, not what it is today, but what it was at the time you made certain decisions. Yes, and that is the reproducibility. All right, so we've talked a bit of different concepts that touch the Lakehouse. But to actually achieve it, Lakehouse has, I'll call it components or layers that determine what data lives at different stages as you're moving towards a certain objective. So generally, let's think of this from, we have a business objective, maybe to forecast something. And to do that, we have a certain set of data. Maybe we control the source that produces it, or we don't. So we have to ingest this data and move it across different preparation stages before it can be used to actually get a forecast out of it. So the core concept here is at the different, I'll use different words, stages, layers, etc. But what you're looking out for is what you're guaranteeing at different stage. So at the earlier stage or at the point of entry of this data into a system, that data, you're just guaranteeing that it's available. So it can be duplicated. It could come as many times as possible, etc. But at that stage, availability is a guarantee. There will be a stage where duplication is a problem. So when you need to guarantee that the data is actually deduplicated, then the data moves to the next stage. And in machine learning, you can build something called features. Features are like signals that you extract out of data. That would also be another guarantee or some kind of quality improvement on the data. That would also necessitate another layer to how the data, the lakehouse is structured. So let's use an example to kind of put things into perspective, and something similar to a summit. Say we have these tables. We have attendees. This is not a virtual summit. This would be if it was like somewhere in a place and where people had to like log in or clock in into, say, a room, etc. And the objective of what we're trying to do is we're trying to predict if the size of the room will actually is it sufficient for the people that might attend? But the way we're doing it is we need to predict if, so say we plan, let's say this room will take 40 people, it will have this particular talk happening. But we're trying to predict for if there might be more people. So just build a very high level system. So we have the whole scanning happening. Someone has a badge, they have an ID, there's a session ID for the session they're attending. There's a time they scanned something and there's a device. We have data about their registration. And then the thing we're most interested in is session change. So say we had planned for 40 people, but we predict that there will be more interest in a given session. So that room has to grow, or we need a bigger room. So the session's room has to be changed. And that's really what we're trying to predict. So we'll use this hypothetical example as we walk through the different layers of the lakehouse. So we'll start with the earliest layer in the process, which is something that is called landing. So here you receive data as is from whatever system is bringing it. So in our example, say we have a scanner at an entrance to a certain room. It will scan, probably maybe sends a JSON, etc. However it works, our landing zone will receive it and store the data as is, like literally bytes on object storage. So that's the first layer. And this layer gives you or guarantees that you can always rebuild this data. So you may not use everything that has come, but you have it. So depending on the business objective that is being answered, you can always either process more of that data, or if anything were to happen to bronze, the other layers that actually depend on it, then you can always go back and replay that data. But what this also tells you is learning can receive the same data as many times as the source system send it, or also your own internal ingestion systems read it. And at this point, it doesn't really matter. The guarantee is that the data is there. Now we start to build more value into this data. Again, value is in respect to what the business objective is. And that brings us to the bronze layer. So this is where the whole lakehouse actually starts. So before we just have regular bytes, this could be really anything, images, Excel files, JSON objects, etc. So in bronze, you start to add structure to this data. But again, at this point, you want to match your source system as much as possible. So there's not a lot of change that you do here. You just add a few guarantees that will probably be needed in the higher levels, things like natural IDs, like the columns that define how unique the data is. Those are things you start to pull out of your raw bytes and adhere. But generally, this is also just a stage to absorb the raw data. And here it doesn't really matter that you have duplicates. What you want to guarantee is that you actually have the data that you're meant to have. You'll see a bit of an overlap between this and landing, but the reason here is really at a certain point, landing most likely be cleared, since it's just a place where data is received and then the upstream processing starts. So you most likely clear landing and move on. So bronze will be the true historical source of what entered the system and what it was at the time it entered. All right, so this is just an illustration of what could potentially happen at, say, at the entrance of a given session. So you have people scanning, maybe the scanner for some reason, instead of sending one record, it sends more than one, send three. Maybe someone scans twice and each time they scan, something is sent. So to bronze, this is very fine. To simply append, it has some kind of logic that will be stored in this particular data payload that the other layers can use to say the duplicate. But at bronze layer, it's again the guarantees we have the data at least once, meaning it can be duplicated or as many rows as whatever the source systems or the ingestions can create. So, but at a certain point, we need to handle the duplication. We need to conform, clean up this data, and that is where the next layer comes in. Now, this layer guarantees that even if, say, at the entrance someone scans twice, at this layer we'll only see that one record. If a change does happen, then again, this layer will guarantee that we'll see one version of that change at this layer. So there'll be like processing logic between bronze and silver that cleans up this data, and you always see the the duplicated layer. So as we follow here, you can see that there are different levels of, I'll call it, quality and guarantees that you're providing as the data is moving through the lakehouse. So at Silver, we also introduced time. So at that point in time, correctness or provenance that we saw before starts to come here through something called an as of date. So at this particular point, I received this data that looks like this. Some change happened, whatever it was before stays, but the new change also gets added. And now, depending on how the person who is querying or the engine executing a query on this defines whatever the time they're looking for, they will see different versions of whatever was stored in those particular layers. So this talk is mostly focused on machine learning. That's why we have a features layer. But in some other workloads, maybe business intelligence, etc., this may not be the key thing that moves on from the silver layer. But particularly in machine learning, most times some features are being built out of the raw data that you have to try and get to some decision. All right, so this is just a demonstration of the whole time travel concept in the context of Silver. So imagine we had planned for a room to have 40 people. And at a certain point, maybe the people that actually came into the room were, in this case, 300. So if you had run the code, say in September, then the code will give you the 40. And if you run it today, you see 300. So same code, same process, but you see different values of data. Now for machine learning, this is a problem because you could have created the model with a 40, and now when you're doing some evaluation, follow-up or improvements to the model, when you do run the same pipeline, you're actually saying 300, which distorts whatever it is that you are trying to do. So what the Lakehouse would give you, again, is that time travel. You would add a snapshot, and the snapshot would be of September, and you'd still see the 40 from that time. And that gives you that whole clarity on the data, like evaluations will make sense, and whatever decisions that were made, your evidence will be the 40 and not the 300, which can be a distortion to the reality. Yeah, so then the concept of time is critical to the Lakehouse. So it's very important to build, I'd call it a helper, one thing that determines how the as of in that system works, so that the different people or different systems that are using this particular data do not all define it by itself. This is just really a best practice approach for ensuring that when I query for data and I want to see what it was in November, sorry, say from the example, I want to see what it was in September, I do not get the results of what it was in November. Yeah, this is very specific to machine learning, but the next layer could be features. Again, like I mentioned, The features are signals that are extracted from raw data that carry some kind of signal that could be useful for predictions. Like in the exact example we're looking at, where people are attending a conference, maybe the name of the conference could carry some kind of popularity index of some kind of interest index. So that could be a feature. Like you get the name, convert it to what is currently trending, and then perhaps you could predict that maybe more people will be interested in such a talk. So extracting the things and then storing them, that is really the features. So you can have as many features as possible in, again, when building models, it's mostly experimentation, trying with as many things as possible to see what actually gives you the predictive power. And at one point, you land on a set of features that will actually give you performance that is acceptable as good for the business objective. And with the Lakehouse, you don't have to store separate data sets for the different sets of the features. You could store all this in one place, and then all you're doing is selecting a certain combination of the different features, and then you can do the training and also do the inference. So the inference is after you've trained and you have a model and it's running, then you're now using it on unseen data to actually come up with the real valuable predictions that are of interest to the business. Then finally, we have the code layer. So the code layer is really the entire point of, it's a deliverable of the whole system, where you have the things that have actually happened and you're using the things to come to some kind of prediction. Yeah, it's called opinions, which is, yeah, you can think of that as I've analyzed this data and I've come down to, I think this is what this data is saying. Depending on whatever mechanism you've used, it could be close to what can happen in terms of like a prediction, or it could be, but essentially gold is where everything from the data that entered into the system from landing, managed by bronze, duplicated at silver, created some signals out of that data, and then you produce something that is of value to the business as either a prediction or a decision, let's go this way or not the other way, etc. But you can see the provenance here. So without a system like this, you'll probably have the predictions and also know what data got into the system, but you'll miss all the stages from how the data was transformed to however it was converted into that decision that you gave. Now, if there ever comes a point where you need to defend this or replay it or reproduce, maybe you want to build a better system, a better prediction system, and you'd like to see what the issues were with the version of data you used, you would not have that. But with the Lakehouse, everything is recorded through the system and you can replay the decision down to the exact event that actually introduced that data into the system. Yeah, there's something of the same point. So data that you use for training used really the same transforms because the place of storage is really the same. It's the same with inference. Inference is after you've trained a model, then the model gets used somewhere in a real world setting where you actually need to now make the decisions. If it's, say, a forecasting thing, in training, you will set it up in a way that you have what the data used to make a forecast of a certain time, and you also have that time to compare that the model is actually good. But at inference time, you only have what has happened, and now you're trying to predict some unknown, which you will know later on in the future. But what the Lakehouse is giving you is the transform that you use for, think of a transform as a pipeline that you use at training time is the same that you are using at inference time. All right, this is the same thing as what I just explained, where let's think of room assignment as a prediction. you can walk it back to the system that, in this case, the raw scan file that actually introduced some data point that led you to determine that assignment. Now, in this particular application, it may not be of a lot of relevance to know about the raw scan, but think of it in like financial systems where you give someone a credit score or maybe a diagnosis of a certain disease. It would be very imperative to know how to give a provenance of the data that actually led to this decision being made. Yeah. So what comes with managing a system like this? So because of the way the storage works, where whenever some new data is introduced into the system, a whole new data file is written. Over time, these files grow. And if those files are big enough, then it's possibly not a problem. But if you're doing a lot of small commits that happen to be very frequent too, then you have very many small files, and this introduce their own inefficiencies. But to manage that, then you'd have to have some maintenance where you combine these files and make them bigger so they can easily be managed. But also, if you're having a lot of frequent small commits and tons of small files, then you might be using the wrong system for solve a certain problem. But that's one cost to look out for. So as files get written, at one point, because there's so many, you need to compress them to ensure efficiency in the system. Then the key defining feature of a lakehouse, again, is the reproducibility. So that means storing snapshots. And whenever you delete a snapshot, then you can no longer replay what the table state was at a certain point in time. So this is something to think about at the design time, where if you need to reproduce something or provide evidence for a certain decision, then you will need to store the snapshots for a bit longer. And if it's something that, yeah, doesn't really need a lot of time, think of like exploratory data analysis, maybe that can be just reduced to days. But if it's financial, perhaps it could be years. But it does have a cost in terms of the size of what you're actually storing. And that's something to consider. The other thing is, so the catalog is think of the catalog as get. It's what maintains the pointer to what the current state of the tables are. That has to always be available. Changing the metadata is also very inexpensive in terms of processing. But if you ever want to update a row in the data, that is very expensive. If you remember from the picture, you'll have so many little files. Let me see if I can go back to it. And that's why earlier on I mentioned, ideally, if the system is more of appending, you're looking at Lakehouse. But if you need to make a lot of row level changes, then you'll need to consider an online transaction processing system. Yeah, then this is what we've really been going through. So if you need to know what state the data was in at a certain point in time, that's your reason to use the Lakehouse. This is mostly useful for machine learning. The table format is simply a manifest that defines a metadata that defines a state of data and moves as a commit in a Git repository would move. The layers that we saw, the bronze, silver, and gold, really just guarantee different things about the data at different stages. The snapshot is what you use to do the whole time travel, go back in time, see what the data was, and then you need a helper to ensure that your point in time joins actually are give you the data you expect at the time you're looking for. So like if I'm checking in November and I need to see what the state was in January, then I should be able to guarantee that that's what I get. Yeah, in terms of tools that you can use to actually achieve this. So the table formats, most of them, I think the popular ones are open source. There is Iceberg, Delta Lake, etc. Then you need the catalog. So a Lakehouse is not one system. It's a bunch of different systems doing different things to bring together this architecture. So you'll have the table format, which is what manages the actual data that is stored, how the schema changes, where the different things are stored, etc. The catalog is the pointer to the metadata of that table format. Then, like I mentioned, so the table formats are not things you can use to query etc. You'll need a query engine, something to actually read the catalog and find the data. So the popular tools in that are like Spark, there's DuckDB, etc. Then again, the table format is simply a definition of how data is stored somewhere, but it needs to be stored somewhere. So a lot of, should I say, teams that actually implement this use object storage, given how cheap it is. And I mean, they could use any kind of object storage from open source solutions to the proprietary ones, like the common cloud platforms. Then you need to think about ingestion. This is how the data will get into the landing zone. You can build your own custom tools, but they're also already built tools like the Bezium, Kafka. Then you need orchestration. So we saw different layers. When data hits the landing, something has to be watching that landing to know to move it from landing to bronze. Same thing happens with bronze. Something is watching and it knows what it needs to do with that bronze to do the deduplication, etc., prepare this data for silver. Once the data is in silver, there has to be something that knows that, okay, now that I have this new data, I need to compute these new features, etc. And now that the features are here, then I can make the predictions. So in a Lakehouse, that is something you can introduce through tools like orchestrators. There are very many that can be considered. Then you want to ensure that there is validation and quality. As you saw in the bronze layer, you don't care so much that data came twice or it's duplicated. But as you move towards the decisions, the predictions that you're trying to make, these things start to matter. So you need to guarantee that there is some quality assurance at the different layers, and the few tools that can be used there, just like you can build some custom logic for that. And for this particular setup, the example was in machine learning, you would also need a tool that manages the features that machine learning uses. Yeah, that was the brief about lakehouses. I hope there were a few things that we picked up. Thank you.
Thank you so much, Moses, for that insight.